All right, you guys, free response question number 5. I really hope you guys are getting these tree diagrams. They help a lot. I know this one was a little bit hard to read, but I think if you can read through it, it makes a lot of sense and set up the tree diagram, then this problem isn't too difficult. So this one says the system's alarm sounds at the central monitoring location if the system detects a security break-in. Tests have indicated that 3% of clients have a false alarm, meaning the alarm sounds when there's no fire. All right, so we got to start with fire and no fire. So it's kind of backwards and it doesn't go in order. So it says that at the end here, 0.1% have break-in fire or smoke incidents. That means that something actually happened. All right, so 0.1%, I did 0.001. And then from there, we have alarm, no alarm. So 3% have a false alarm here. Oh, wait, so that's on the no fire, would be a false alarm. And so this should be 0.999, 1 minus that. And that'd be 0.03. So that means no alarm is 0.97. Okay. Then it says the alarm sounds when there's no incident, and that in approximately, let's see, 0.5% of actual incidents, the system fails to sound an alarm. So we want there to be an alarm, but it fails to do that. So that would be the no alarm, which is 0.005. And 1 minus that is 0.995, where it correctly alarms. All right. So then this says, what's the probability the alarm will sound? So the alarm will sound right here. We're going to multiply that times that. Or the alarm will sound right here. We're going to multiply that times that and add, and we get 0.031. All right, this formula is on your yellow sheet and given on the AP exam. So suppose the alarm is sounded at a client's premises. So that means we know the alarm went off. That's the given part, okay? This bar means given. We know this happened. What's the probability there was no break-in, smoke, or fire? All right, probability of no fire. So we want the probability of no fire and the alarm went off divided by the probability of the second thing. So no fire and the alarm went off is 0.99 times 0.03. And in the bottom is all the pathways to alarm, which we just did. So any way that the alarm could have gone off is 0.031. And that gives you 0.967. All right, number 6. So does the data provide any evidence to support the physician's theory? So if it's a yes or no question, then it's looking for a significance test. So first we need to know what kind of significance test we're doing. The reason that we want to actually calculate the difference here and do it as one sample is because it's the same mother with both kids. So remember, if you have the same subject doing both things, then it's best to use the matched pairs or the paired t-test. It's still just a one sample t-test for means. So you actually do not want to do the 2 sample test, which I'm guessing some of you guys did. We want to find one sample and do the difference. So we're going to start with our state. So the null hypothesis is that mu d equals 0. So there's no difference between the birth weights of the first child and the second child. And the alternate, if you did greater than, that could work. Just depends on what order you subtracted in and how you defined that. So I said mu d was mu1 minus mu2, where mu1 is the birth weight of the first child and mu2 is the mean birth weight of the second child. So I'm looking for the second child being bigger, meaning a negative number if I'm subtracting in that order, okay? You can call this a paired t-test, or you can call it a one sample t-test for means. And we're going to check our 3 things. So we have a random sample, of 19 mothers. For our 10% condition, there's at least 190 mothers of 2 children. And we're going to check normality. So we only had 19 subjects, so that means we need to check the graph. So first of all, you got to plug in your data. You can go through and subtract them all ahead of time, or you can plug in the data first and second. And remember, this one you can call difference, and you can write or type an equals in right here. And as long as you type them in exactly how you titled your column, so first minus second, it should subtract for you. Okay, so now I'm going to do everything with just this difference column, so it's one sample. So first I want to go control plus page. I'm going to add data and statistics, and at the bottom here I'm going to put difference. You can do box and whisker, or you can do the normal probability plot, which I'm going to do the normal probability plot. Okay, make sure you sketch a nice graph and you label your x and y axes. So you need to label difference and expected z and make a nice graph for the AP exam. All right, so this is called the normal probability plot, is roughly linear. Therefore, we can assume normality. All right, then we want to actually run the test. So let's go back to our data. We can do the test right here on our spreadsheet. So go to menu, statistics, go to stat tests. This is just a t-test, all right? It's one sample. There's no paired t-test on here, so it's still just a one sample t-test for means. We do have data this time since we have that list. Press OK. Our null hypothesis is that there's no difference. And our list, we want to put what we titled it. We're looking for less than when we subtract. So we have our t, our p-value, and our degrees of freedom. This is the minimal work right here that you can show along with the name of the test. But ideally, you remember the formula. So we're finding a test statistic, which is the statistic minus the parameter over the standard deviation of the statistic. In this case, the statistic is what we got for our mean, our sample mean. So our sample mean is this number right here. And we're subtracting the parameter, which is the null hypothesis of 0, over our standard error formula. So we got to look at S sub x divided by the square root of 19. Okay, that will give us the t value, negative 4.059, which then we should shade on our normal curve. Okay, our p-value comes from TCDF, from negative 1,000 to negative 4.059. Degrees of freedom is 18, since our n was 19. Okay, that gives me a p-value of 0.0004. All right, so then we need to conclude, because the p-value is less than 0.05, we reject the null, which means there is convincing evidence that babies are heavier at birth than their next oldest siblings. All right, so that second child is heavier than the first child. Okay, describe the relation between the birth weights of firstborn children and the birth weights of secondborn children. So this is your DOFs, direction, outliers, form, and strength. Also, there's a sentence for this on your top 10 phrases that pay. So there is a strong, positive, linear relationship between the birth weights of the second and first child, and there are no outliers. Okay, this is our residual graph. So now it says, is there a significant relation between the birth weights of firstborn children and the birth weights of secondborn children? So this is your significance test for slope. Is there just a relationship? It doesn't say which way. So your null hypothesis, and I don't know why I don't have H naught right here. There we go. And H sub A. So your null hypothesis would be that B, capital B, your slope is 0, so there's really no relationship. Your alternate is just that there is a relationship. We're not saying positive or negative on this one. Where B, capital B, is the slope of the regression line for the weight of the second child as a function of the weight of the first child. This is called a t-test for beta, or slope. We're going to check liner. All right, so remember, liner is the acronym you need to know for this test for slope. So for linear, we can say that there's no leftover pattern in the residual. All right, looks like random scatter. For independent, we just check 10%, so there's at least 190 moms of 2 kids. For normal, we already did the normal probability plot, so it's roughly linear, so we can assume normality. Equal standard deviations, you're looking at your residual plot and kind of how far away these points are from this 0 line. And so the residual plot shows roughly equal scatter around the horizontal line at 0 for all x values. And yes, we took a random sample. So where to do the t-test for slope? You can just find a blank box somewhere over here and go to menu, go to statistics, go to stat tests, and this is the, oops, hold on, menu, statistics, stat tests, and we're looking for linear regression t-test, okay, A. So then we plug in our x and y list. So my x list is going to be the first child, and my y list is going to be the second child. And we're just looking for not equal to. And press OK. So we need the t, okay, our test statistic. We need our p-value, and we need our degrees of freedom, which in this test is n minus 2. So it is 17. Okay, that's all I'm showing on this one, just t, degrees of freedom, and our p-value. Now be really careful with your p-value. So this looks like it's 2.86, but if you hover over it, it's actually got this little e to the negative 10. You would not know that unless you carefully checked. So be really careful on the AP exam that you check that those don't have scientific notation, because that is basically 0, which makes a difference on your conclusion. All right, so because the p-value is really small, it's less than 0.05, we reject the null, which means we have convincing evidence that the slope of the regression line between the birth weights of the first and second child is not equal to 0. All right, so for this one, we're predicting the birth weight of the second child. So they already gave us this output right here. We just go to this data. This is the constant, and this is the slope. So you want to write it in that order, constant plus slope times the first child. And remember, you have to have this hat on top of this second weight. That means it's predicted. And I'm going to plug in, if the first kid is 7.2 pounds, that means the predicted weight of the second child is 7.47 pounds. For part E, approximate range of birth weights of second-born children whose firstborn siblings weighed 7.2 pounds. So a range for that second child. Well, here's our predicted output, right? But we can be 95% sure if we make it 2 standard deviations within that number. Then we're 95% sure we're going to capture all the babies second-born where the first one weighed 7.2. And the second one weighed 7.47. So the standard deviations comes from right here. All right, so I want 2 of those so that I can be 95% confident. So I'm going to add and subtract 2 times 0.3772 to get a confidence interval or a range. From 6.72 to 8.22, we're pretty sure, 95% sure that second baby is going to weigh somewhere between there. Okay. We could do 3 standard deviations if we want to be 99.7% sure. And so we would add 3 times that and get 6.34 to 8.6.